Okay, so I'm going to start on the second objective here in alternators. Going to go through the theory part of it, and then we'll do some examples here on camera too. Okay, so just like we talked about generated voltage in a DC generator, okay, and we did talk about the generator effect in a DC motor as well. We basically have factors that we want to talk about because there's only certain things we can affect to change the generated voltage. Okay, so rather than just have the windings are this and this is the induced voltage and it never changes. Okay, we can't have that because as we put load on an alternator, the voltage is going to change because of that. Okay, so we definitely have to have a way to regulate our voltage to maintain that phase voltage or line voltage, or what they would call in this aspect here we're going to talk about called terminal voltage. Okay, so that's where you'd hook your load up to. It has to be a certain rating because that's what our equipment is rated to be hooked up at. So how can we or what are the three factors that affect our generator voltage? Again, this is of the alternator itself, the number of armature turns per winding. Again, something that's made in the machine, so we can't really alter that guy that much, I would say, and definitely not on the fly. The speed of the rotating field, again, we want to have that thing running at a fairly constant speed. The amount of flux produced by the rotating field. Okay, so again, just like we talked about in DC, that's the one that we could potentially change. Okay, if we can change the amount of flux produced, and that flux is basically rotating within those armature windings, we could potentially change the amount of voltage induced in there. So the only practical way to change the value of voltage generated is to alter the field flux, again, as the other two factors are set once it's constructed. So what does the field flux depend on? Well, it depends on the number of turns in the field winding, the type of core material, and the amount of current going through. Again, out of these three, the only thing we can adjust is the amount of current flowing through the field windings. Okay, just like we talked about in DC. So we can affect the amount of current going through the field, which affects the field intensity, and that will affect the generated voltage. So the only factor that can be altered, again, is the amount of current, also known as field excitation current. Okay. So the output of an alternator. So again, the output is basically what we're generating to use to hook our equipment to. So an alternator output is affected by the load it supplies. A change in the load changes the current supplied by the alternator, again, if the power factor remains constant. And it changes the alternator internal volt drops due to three factors. Okay, so we're looking at this on a phase value. Okay, so those windings actually have volt drops in them due to the resistance of the armature conductor, so the windings themselves, the inductive reactance of the armature coils, because as soon as we have a coil, we have that XL portion of it, and then armature reaction, so the distortion of the main field flux due to the armature's own magnetic field. So at no load, there is no current flow, and the generated voltage on the armature winding equals the terminal voltage. So again, if I'm generating, let's say on a phase level, I'm generating 277 volts. If I don't have load on there, then my terminal voltage will be 277. So if I put my meter on the terminals, I'm going to read 277 volts. As load is added, the resistance, reactance, and armature reaction produce volt drops that cause the terminal voltage to be different than the generated. The generated could be higher or lower depending on the power factor of the load. Okay, so we're going to do some questions here in a sec that will prove all that. Okay, but we basically just want to see that as we're adding load, something's got to give. We're either going to have to increase the generated voltage or decrease, again, depending on the power factor. But this is going to change. And we have to change that on load because there's current flowing through here now. We're going to get a volt drop across the resistive portion and the reactive portion of this winding. And that's going to affect our terminal voltage output. Okay, so if we keep loading it up, our terminal voltage is going to change to a point where it's not usable anymore. So if I put too much load or a certain type of load on there, I could have a significant drop in terminal voltage, okay, or a significant increase in terminal voltage, which again would be detrimental to the loads hooked up to it. So we're going to look at this on a phase level again. So here's our rotating field. Here's the E-gen portion of it. Again, this is for each winding here. We'll look at it per winding, per armature winding. This terminal voltage, think of this is like a phase voltage, because these are like our three phases that we're going to have spinning around, or sorry, stationary, while we have our magnetic field spinning around, inducing a voltage in them. So they talk about the gen, the resistive portion. They did say the X arm, okay, and then the armature reaction. What they're saying is these have the same effect on the terminal voltage, and they're proportional to armature current, both of them. So what we're going to do is just combine the X arm and the armature reaction to something called synchronous reactance, and just use the term X sync for it, okay, as opposed to N sync. Oh, just kidding. So we have our generated, then we're going to have a volt drop across the resistive portion, we're going to have a volt drop across the reactive portion, and then our terminal voltage, or our phase again, that's going to be affected by that. And so here's the two scenarios. We either add load on them, and then we change the field excitation to potentially generate more or less voltage to maintain this terminal voltage. If we don't, and we keep the E-gen the same, we'd see an effect on this terminal voltage. Okay, when we do our lab, that's what we'll see. We'll see what happens when we add an inductive, resistive, or capacitive load, and what happens to the terminal voltage when we do that. Synchronous impedance, they mentioned in your module, is the product of armature resistance and synchronous reactance. So there's your armature resistance, synchronous reactance. We don't use this in our calculations, just saying you can use the synchronous impedance of the alternator to calculate the maximum short circuit current available from the output terminals under fault conditions. Circuit protective equipment is sized based on the maximum short circuit current, so you might need that value to size your fuses or breakers. Okay, and then we talk about voltage regulation. So we talked about speed regulation. It's literally the same formula. It's just now we're talking about voltage regulation. So no load minus your full load over your full load times 100 is going to give us that percent. Again, no load, again, where we have literally no load hooked up, so our E-gen would be equal to our terminal voltage. Okay, our full load is going to be obviously when it's loaded to the probably to the rated current, and then we will find the difference between those two, divide by full load, and then we'll get our percent. Okay, so this is the question that I'm going to go through. What it does in your module is it goes through every scenario. It goes through unity in one example, then it goes through lagging power factor, and then a leading power factor. So I'm just going to kind of do it. I'm just going to switch my camera over here. I'm going to kind of do it in one shot, just so we can compare things a little bit, potentially maybe a little better. But this is how I would do it on the board if we were face to face. So I'm just going to start my camera. Okay, so this is the question that's in your mod again. Hopefully you can read that. I'll zoom in a bit here. Okay, so 3 pins here. So we want to calculate, so we got 100 kVA load, and obviously connected in Y, because that's what it says in the mod. They want us to calculate the percent voltage regulation from no load to full load, and we're going to do it at unity, we're going to do it at a lag of 0.8, and then we're going to do it at a lead of 0.8, and then we're going to compare. Okay, so they told us that it's a 100 kVA machine. The resistance of the armature winding is 0.1 ohms. The X sync is 1.0 ohms. Okay, so first thing we're going to have to do if we want to find out how load is affecting it, we need to find out the current of the load. So I'm going to take my 100 kVA, so 100,000 VA, okay, and I'm going to find my line current for that. So I'm going to take, I know this is, if it's 277 on a phase level, it's going to be 480 volt on a line, again times root 3, because it's a 3-phase machine. So I find my current and it should be 120. Let's just say, I'll say 0.281. Okay, so that's my I line. Now again, we're hooked in Y, so that is also my I phase. Okay, so that's the current that's going to be flowing through each one of these windings. Okay, so each one of these windings has the resistive value and the X sync value, each one of them. But we're just going to look at one winding. Okay, so I want to just make another little note here again. This VT that we're going to be talking about, this is terminal voltage. But I also want to say we could also make sure we have an understanding that that's a phase voltage as well too. Okay, so let's work on the unity. So let's do unity first. Okay, and we're going to talk about the you'll use the exact same way they did it in the module, so we can kind of relate back to that. So we have our winding that has a generated portion, a resistive portion, an X sync portion, and then my terminal. Okay, so if we're going to label these, it's going to be my E gen. It's going to be a volt drop here due to the resistive portion, and then I'm going to have a volt drop due to the X sync portion, and then this is going to be my VT, or my terminal voltage. Okay, so again, the goal of this is to maintain our terminal voltage. So we want our terminal voltage to be 277 volts, okay? Because that's, again, our nominal voltage we need for our equipment. Now, they gave us some resistive values for these, okay? And then we're gonna find out what the generated voltage we need for when there's this much current going through the winding to maintain that voltage at our terminal. Okay, so our Vx again was 1.0 ohms. And my X sync, sorry, my X syncs, yeah, we already did that, Vx, sorry. My armature, so the volt drop due to the resistance of the armature, sorry, is 0.1 ohms. Let me just brain fart there. So I want to find out what the volt drops are across these guys. So if I use this current, I'm going to go 120.281. So 120.281 times 0.1, and I should get that 12. So I'm just going to say this is 12 volts. Okay, so that's my volt drop there. And I might just round just to make life easier here, just for this comparison. But again, in our bank, go to 3 decimals. So when I take this current, 120.281 times 1, obviously I get that. Just had to make sure and do that calculation. Let's round that. We'll say it's at 120.3 volts. Okay, so that's due to resistance. That's due to synchronous reactance. Okay, so now we would just use Kirchhoff's law here, where we're like, well, all these volt drops are going to have to add up to our gen in order to get that voltage at the end. But we want to make sure that that we're adding these properly. They're not all in phase, okay? Because this is resistive, this is reactive, and then this guy, it's important that we talk about here that we're at unity, okay? And we will talk. So I'm going to first go and reference this to a phasor diagram, where again this is a series connection where we have different volt drops. So current would be my reference here, so my I phase in that case. And then I'm going to plot these voltages against this current. So the 277 is a terminal voltage. Well, if I'm at unity, I know that this phase voltage is in phase with the current. So my 277, or my VT, is going to go right there. So I know he's at 0 degrees. Okay? Now I look at my Vx. Well, I know if it's a synchronous reactance, okay, or it's going to be at 90 degrees. So I'll put that guy up here. So this is my Vx. Okay, so this is going to be at 90 degrees. And 90 degrees up there because we're showing current lagging. Okay, so in an inductive circuit, current lags. So that's why we're putting the Vx up here. Again, at this 90 degrees here. Okay, Then the resistive one, again, it's purely resistive, so no leading or lagging on this portion of it. So my VR is going to be right here as well, in phase at 0 degrees. So when I want to find out the generated voltage, I'm just going to add all these up vectorially. Okay, so if I go 277 DMS 0 plus 120.3 DMS 90 plus 12 DMS 0, and I get 313.04 volts. Okay, so again, and I could toggle through and find out where that guy's sitting too if I wanted to know that, just by going second function comma or second function exponent. So it's sitting at 22, so it's like sitting right there. Okay, I'm not gonna, well, I guess I can, why not, for funsies. Okay, so that's where he would be showing that 22 degrees right there. Okay, so this would be my E-gen on the result. Now, what this is saying though is that in order for me to maintain this voltage of 277 on my terminals, I have to generate 313, again 0.04 volts, in order to take into consideration that I'm going to have a volt drop here, and then I'm going to maintain this at 277. Again, this is at unity, and I would say under full load because we're using the rated VA here. Okay, so now we look at the voltage regulation on this. So we kind of, when I talk about the voltage regulation, I think of the no load, I guess, as the E-gen. And I know it kind of gets, when we do our lab, a lot of guys are kind of confused as to why we're using the E-gen as our no load, but we kind of look at it as, so again, just to rewrite this formula here, we have our voltage of our no load minus our voltage of our full load over our full load times 100, and that's going to give us our percent voltage regulation. Now, what we kind of look at is under no load is our E-gen, okay, because we're kind of think of it as if, you know, if I didn't have a load, or say I had this load on and everything was adjusted, okay, I'm generating, I've increased or decreased my field excitation just enough to get this 313 volts so that I can generate and deal with these volt drops and still have my terminal voltage. If that were to potentially, you know, come off, I guess this would be my no load voltage now, because it says your terminal voltage and your E-gen under no load would be the same. Okay, but again, this is under full load. That's how we got these volt drops, obviously, or we wouldn't have been able to. So I kind of look at it as E-gen and my no load. So I take my 313 and I'm going to subtract my full load, which would be my 277, divide by my full load again, times 100, and I get 12.996%. Okay, so that's the voltage regulation for this current, or this load, at unity. So now we're going to look at the next scenario, which is going to be a lag. So we have a lag of 0.8. Okay, or we change that to an angle, and it's going to be 36.87 degrees. Okay, so we're going to do the same thing now so we can compare. We're going to use the same full load current, but we're going to change the power factor just so we can see what happens to our E-gen when we do that. Okay, so I should be able to continue to move up here. Again, we're going to get some of the same values. We're just going to potentially change where they are located. So I still have my, draw this out the same, got my E-gen, got my resistive volt drop, my reactive volt drop, and then my terminal. So VT, X sync, VR, and E-gen. Okay, so some of these values again, I still want to maintain that 277 volts on my terminal. I'm going to get the same, because we're using the same load, so I'm going to have the same current, so I'm going to see the same volt drop. So I'm still going to see 120.3 volts here. I'm going to see 12 volts here. And this potentially is going to change because we're not at unity anymore. So if we go to our phasor diagram, again, still series, so this is still current as my reference. What I want to do now is say, well, if I'm at a lag of 36.87 degrees, I know that lag happens on a phase level. Okay, so this is my load now. It's drawing the same current, but now it's at a lagging power factor. So to show current lagging by 36.87, I'm going to put my terminal voltage right here, where this is going to be 36.87. So he's not at zero anymore. It's at 36.87 degrees. Okay. Now the X sync still at 90. So Vx, that's still going to be at 90 degrees. And our resistive volt drop is still going to be, VR is still going to be in phase with the current. So this guy's still at 0 degrees. So now when we add these phasors up at their respective positions, I go 12 DMS 0 plus 120.3 DMS 90 plus 277 DMS 36.87, and I get 369.66, so 369.66 volts. Okay, so if we're just looking at the difference right now between our generated voltage, even if I get a lag, okay, I'm going to have to generate more voltage than I do when I'm at unity. Okay, just because of the phasor location now, in order to get those total voltage, that total voltage, I had to add them out again at their respective angles. I'm actually having to generate more voltage for this lagging load. Now, when we go to our voltage regulation, so we'll take our 369.66, and we're going to go minus 277 volts divided by 277 volts, and I get, sorry, times 100, and I get 33.45%. Okay, so then my voltage rate, I got a greater no load to full load range too, and we're seeing that in the percentage as well. Okay, so now let's look at the last scenario, which is our lead. Okay, so our lead, and we're going to do a 0.8 as well here again, which is 36.87 degrees. Okay, but something just to kind of look at before we move on there is these didn't change. Okay, they're not going to change. They're constant. Again, the value of them didn't change because we're using the same load for each example. But more importantly, or equally as important, is that their position didn't change. Always at 0, always at 90. It's the terminal or the phase voltage that's going to change if I have a power factor. Okay, so we'll look for that here in this lead as well. So again, start out, I'm going to draw my same diagram. Again, you've heard me say this before, but I draw things out the same way every time. Again, quick, dirty, whatever you want to get, just to give yourself a visual reference. It definitely helps out when you're doing repetitive questions to do them the same every time. Okay? It just makes our lives a little bit easier. So again, terminal voltage 277, using the same circuit that we've been using for the previous two examples. Then we can get a nice comparison because we didn't change the load on it. Our Vx again is going to be 120.3 volts. Again, because we didn't change the load. 12 volts here of resistance. And then we're going to get a different generated voltage again this time. Okay. So again, these didn't change. So this is at 0. This is at 90. Now this guy's different because we have instead of a lag, if we go to our phasor diagram, again, current being our reference, because it's a series, one piece of wire, okay? I'm going to have my Vx up here, I'm going to have my VR in phase. Now I want to show current leading this phase voltage by 36.87. So I'm going to draw it down here this time. So my V terminal, and show this right here is 36.87. So when we're adding this, you could either, again, just like we talked previously, you could say it's at negative 36.87. I like to reference from 0. So I'm going to say 360 minus 36.87, and I get 323.13. Okay, so that's where that guy's sitting now with our lead. Now, when we add these vectorially, we can get our new E-gen for this leading load. So if I go 277, DMS 323.13, okay, plus 120.3, DMS 90, plus 12, DMS 0, and I get an E-gen of 238 volts. Okay, which seems crazy now, but it's because we are in a lead. We're actually generating less volts than we need at our terminal. Okay, and it's going to affect our voltage regulation as well. So if we take 238 minus 277 divided by 277 times 100, we're going to see the effect. So 238 minus 277 divided by 277 times 100, and I get negative 14.08%. Okay, so can our percent voltage regulation be negative? Why, yes, it can. Okay, so we're going to go through and we'll definitely, this is what our lab is going to be on tomorrow. Okay, so we'll prove these theories here, but I just wanted to kind of get it all in one page so that we can compare. So again, unity, lagging, leading. Our E-gen, look at the difference that's happening. This is our unity. It's increasing for our lag. It's decreasing here. We're actually not going to maintain our terminal voltage in our lab. So we're going to have a consistent E-gen, and we're going to see what happens to the terminal voltage in our lab. So kind of a bit of a flip on the concept, but will be a nice kind of come around, I think, to get the concept out. Okay, so the last thing they talk about in your mod here, I'll just switch back to my PowerPoint, just talk about how we do that field. And I'm just going, don't know where I'm going apparently. So I'm just going to go here, current slide. So they talk about field excitation sources. Basically what we've talked about and mostly what we've seen are these external DC supplies. Okay, again, the amount of voltage is controlled by the amount of DC excitation current flowing from the rectifier. So this is a rectifier, it's a diode, that's what they're showing there, to the field through the brushes and slip rings. So this does still have brushes and rings. A control system adjusts the voltage of the DC external and thus the amount of field excitation. So this is kind of what we've been talking about so far. Then we have self-excited, which basically we could have there's a brush type, okay, where we have another little kind of DC generator mounted on the same shaft as the rotating rotor. So here's the alternator portion. And then we got this little DC generator that's going to generate a DC voltage that we're going to use to excite the field. And then we can adjust that as well too with that voltage adjuster. Then they talk about brushless, okay, so it does not have brushes, it's like our new cordlesses and such. So instead of brushes and slip rings, they use a rotating rectifier. And what this does is turns AC into DC. Okay, so we have exciter diodes, okay, that are going to basically, that's where we're going to be able to control it. And then we're going to have the AC coming out of here because it's rotating in a 360-degree field, and then go to DC, and then that's what's going to go to our actual field here that's rotating through our armature windings, and then here's our output for our connection. So the exciter rotor and the full wave bridge rectifier are mounted on the same shaft, supports the main alternator rotor, and rotates simultaneous with the rotating field of the alternator. So it rotates all on the same field here. Once the prime mover is started, the DC output from the rotating rectifier provides excitation. Okay, and we do get adjustment here based on these exciter diodes. Voltage regulators, again, we need to be able to change our generator voltage based on load. So below it shows a simple type of manual rheostat. That's kind of what we'll be doing. That's what we have anyways. the terminal voltage drops below an acceptable value, again, as we add load, it's going to drop our terminal voltage. So we have to generate, again, if we're talking about a lag or a unity, we're going to have to generate more voltage to maintain that output. Okay, so that's done with a rheostat. Again, increases the current flow to the rotating field, which then induces more voltage, so we'll increase our Egen. Then they also have this solid state, which is basically an automatic voltage, or AVR. So a small portion of the armature current is fed back to exciter diodes. That's these guys here we showed in that previous picture, to rectify the AC supply. So this is coming right from the alternator back into these diodes to the exciter field. That's this right here. These four diodes are usually part of the automatic voltage regulator. A feedback or sensing system monitors the alternator output voltage so that the terminal voltage comes back to this sensing system, okay, and controls the amount of current that is rectified by the diode. So then it's going to say, hey, I need more or less voltage, and it's going to control the current going to here. The voltage of the rotating exciter armature is regulated by the amount of current in the field. Okay, so right here. The rotating rectifier then converts the controlled exciter voltage to DC. So this is the rotating rectifier portion. That's taking the AC that's being generated here and putting it to DC to our field that's rotating within our actual alternator armature windings. So then the controlled DC adjusts the current in the alternator field, which adjusts the alternator output. So again, just constantly reading and feeding back to the system. Hey, my terminal voltage dropped, increase the current, generate more voltage till it maintains. Okay, and that's going to do that automatically. So a lot nicer, obviously. All right, so that's paralleling. We'll do that next video. So yeah.